Okay, here we are to talk about one-dimensional motion, or in particular, we're going to talk about distance and displacement and the difference between the two and how it's going to play a role in physics. Okay, what the most basic way to describe an object's motion is position. Okay, we do this all the time, and we're always calling people, where are you? Where do you want to meet? And we always specify positions. Well, are you here? Are you there? And that tells us a lot about an object. It tells us where they are, what they're doing. In fact, even when somebody's traveling and you call them and they're on I-15 and you ask them where they are. Oh, I'm on milepost 87, or I'm at such and such location, or I'm at such and such city, I'm at such and such exit or turnoff. You never actually explain to them, I'm at such and such turnoff, but only going 10 miles an hour. We automatically assume that they're going a certain speed, and we don't need to understand that. We just want to know where you are, and then we can gauge about where things are going. So to measure your position, we have a few ways that we measure position. Okay, one, we measure in distance, and we signify that with a lowercase d. Okay, that's going to come up when you talk about the other one. And that's just how far you've gone. What's the total distance you have traveled? It doesn't matter the path you've taken. You know, we do this a lot. We talk about running, going and exercising, and sometimes you're running on the treadmill. We still ask you what your distance was, and we expect you to tell us how far you ran on that treadmill, even though you didn't actually change spots. Okay, displacement. Notice that over here we have signify it using a uppercase D. Okay, so when we're talking about things and I want you to worry about the distance of an object, we'll signify that with a lowercase d. If I want you to worry about the displacement of an object, we'll use an uppercase D. That way you kind of understand, if you're not around, what we're talking about. Okay, now these two are similar but different. Okay, displacement is how far are you from where you started. Okay, so it doesn't matter the path you took. Okay, it doesn't matter at all. In fact, to find displacement, you take your final position and you minus that from your initial position. And that's, of course, if we're traveling in a straight line. We'll get into, later on in this screencast, we'll get into how to find your displacement when we're not in a straight line. Okay, but let's take this little diagram here. Distance matters. So if we notice the path taken here is in purple, distance matters, this path that you took. You know, maybe something was in a way. Maybe this was a park or a lake, or you were just doing something and this was the path you had to take to drop off some newspapers or whatever it may be. Displacement, on the other hand, does not care the path that you took. Displacement just cares how far are you from where you started. So in this case, we started here and we ended here. The quickest way to do that is going in a straight line. The quickest way between 2 points, once again, is a straight line. So we started here and we just moved down. Okay, that's displacement. We didn't actually go there, but that's how far we are from where we started. Okay, and we always measure this in meters. Okay, once again, we're just going to use meters as our unit. Very basic, very easy to deal with in physics. So let's talk about when these quantities are the same. The only time you're really going to find that these quantities are the same is if your path and your displacement is the same. But same as in it hasn't been repeating. Obviously for distance you can go up and back, up and back, up and back, and up again, and your displacement's that same thing, but you travel a lot farther distance because you went back and forth. Okay, so usually it's just in a straight line. We haven't deviated from that straight line, and we haven't gone up and back. It's just forward. Okay. When are these quantities different? Pretty much any time else. Okay, whether we've gone around in a circle, whether we've taken a crazy path like it is here, okay, and pretty much anything besides traveling in a straight line or not moving at all, are they going to be different? Okay. All right, so let's talk about distance and displacement. Once again, we have our wonderful little picture up there. Distance is what we call a scalar unit, meaning it's just a number or it's magnitude. It tells us how big something is. Okay, it doesn't tell us anything else. If I asked you how many miles you ran this morning, you could say, oh, I ran 4 miles. That tells me how many you did. It's just a number. It's just a magnitude, just how big it was. I didn't know which direction you went. I don't know if you went north, south, east, west, if you went around in a circle, I don't know. The scalar is just a number, okay? Now, displacement, on the other hand, is different. It is a vector, and so we got a little vector here, okay? And a vector, just like this guy here, is magnitude and direction. If you remember, the Despicable Me movie vector here says he commits crime with magnitude and direction. Okay, that's how you can kind of remember. So not only are we including part of the scalar with the magnitude, but we're including the direction we went. Okay, and that may be that we went up, down, left, right, out, in, who knows, but we included direction. Okay, and we signify those by using arrows. So all these tell us certain things. We were going this way at this magnitude, or up and to the right with this direction, this magnitude. Okay, it tells us both. This is when you can have a negative number. You can say, I ran negative 40 miles. If I know that the negative displacement is to the left or to the right or to the south or to the north, I know which way you went. So let's say I signify that north is positive, south is negative. And I said I ran negative 40 miles. I know I ran 40 miles to the south. A long ways to the south, more than an Ironman, but still, I ran to the south. And it told me the direction you can do. Now, we have this practice little problem here. We have the total distance and total displacement. Okay? And if you notice this, we have t equals 0 minutes. So here we are, starting right here. Okay? And then we go 40 meters this way, 100 meters, and then another 40 meters till we get to time equals 1 minute. So it takes us 1 minute to go 40, 100, and then another 40. Okay, once we reach B, okay, then we go back to time equals 2 seconds, which happened to be C. So then we go back 40, back 100 to time equals 2, and then at D we go back another 100. So our total distance and our total displacement is different. Our displacement, we only started here and we ended here. So that's only 140 meters, 40 plus 100. However, our distance is a lot more. We went 40 to 100 to another 40. That's 180 meters right there. Then we went back 40, back another 100. So we went up to 280, 320 meters to here. Then we went another 100 meters. So we ended up with our total distance of 420 meters, which is a lot longer than our displacement, which was only 140 meters. Okay, so there's times when you're going to want to use distance. There's times when you're going to want to use displacement. It just depends on what we're really looking for in the problem. There are two different things that can give us two different answers. Okay, let's talk about a circle now. Okay, if you go in a circle 3 times, what is your total distance and final displacement? Okay, now this is where, displacement comes in handy, especially if you have one of these questions on a test. I'm sure you'll love it. Because if you start here on a circle and you go around 3 times, we go around 1, 2, and a third time, and where are we at? We have ended right where we started. So our final displacement is 0 because we're back to where we started. That's a wonderful problem. You don't have to figure anything out. Oh, you're back where you started. Your displacement is 0 meters. Now, if we were to find the distance, that's another story. We'd have to use the equation, the circumference equals pi times the diameter. So if you times pi times the diameter, we know the diameter here is 6 inches. Okay, we times that by pi, which is 3.14, which gives us roughly around 18.6, 18.5. You times that by 3, because we're going around the circle 3 times, you're going to get around 56, 54, somewhere in there. Okay, and that's a lot bigger than 0. Okay, so these two are going to be different. This triangle here, this is going to be become our best friend. Once again, we're finding out total distance and our final displacement. The path that was taken is the blue line. This one is very easy to find the displacement. You just add up the path you took. So I walked 8 miles this way, then I walked 15 miles this way. That's a total of 23 miles. But remember that displacement does not care about the path that was taken. So the quickest way to A to B is in a straight line, which is right through here. Now, if you look at that green line and you count in the purple lines here, you'll notice that it is a right angle, and this gives us a triangle. So we can use the Pythagorean theorem to find the distance of this green line. So if we do 8 squared plus or a squared plus b squared equals c squared, and we plug in 8 miles and 15 miles in for our a and b, we get 8 miles squared plus 15 miles squared, which is 64 plus 225. We add those together, we square root that from the c squared. We come out that our final displacement is in fact 17 miles. Okay, so we're going to use this Pythagorean theorem lots. It's important that we remember it. If you don't have this, I'd take a moment to jot this down in your notes. It is also on your reference sheet. If you look on that, there's a reference there for it. Okay, but a squared plus b squared equals c squared to help you kind of know which side of the triangle we need. Okay. All right, so let's do a little practice problem here with Jimmy. Jimmy was lost in a field. This is our first time we've met Jimmy. He found a bottle labeled "Drink Me," and then proceeded to stagger around the field following this pattern. He traveled 12 meters north, 8 meters south, 5 meters east, 20 meters north, and 5 meters west. Okay, so my question to you is, what distance did he travel, and what was his final displacement? Okay, I'll take a moment, pause the video, go ahead and figure this out, and then we'll continue on. Okay, so let's go check your answers here and get what distance did he travel. The easiest way with distance is just add them all up. So 12 meters, 8 meters, 5, 20, and 5. We add all those up. We come up to our distance equaling 50 meters. Okay, now displacement's a little different. We've got to figure out where he went. Okay, so our displacement, we have to figure out how far he went up, back, left, and right. Now let's just take it and do this in terms of arrows. So he started up and he went 12 meters north. Okay, then he came 8 meters south. So if we were to stop right here, we could see that in fact our displacement is only 4 meters to the north. We went up 12, back 8. That's a total of 4 meters from our starting point. Okay, but we got to keep going. We go 5 meters east. Now we could figure out this. We could plug in a triangle and figure out what this is. But let's see what happens. Okay, 20 meters north here. So we were at 4. Now we're up to 24 meters from our starting point, plus over a little bit. And then we go back to the west 5 meters. So these two, see, they just kind of cancel out. We're left back here in the start. And we found out that that was, in fact, 24 meters. Okay. And Jimmy then staggers around the field. All right, you know, we have, once again, we have a foxtrot. Here's the play. You go 40 yards downfield, turn left and go 20 yards, then turn right and go 25 yards, then turn right again and go 30 yards. You know, he goes on and on and on, and sometimes it's a funny joke, sometimes it's not. I thought it was funny. I laughed. Okay, but what we're going to do is we're going to take this here and help us solve the problem. What if it doesn't end up exactly in the middle like it did with Jimmy? Okay, so we're going to start here. We're going to go up 40 yards, then 20, then 25, and 30. So we're going to follow a few rules. Okay, and that's what these few rules will help us build a triangle that we can work with. Okay, the first rule is we need to combine all the up and down vectors. Okay, and the second rule is then combine all the left and right vectors. Okay, then we'll use those to build our triangle, and we'll put the Pythagorean theorem to good use. Okay, so we first started with going 40 meters up. Okay, that's our first up arrow right here. Okay, now the next one that's up and down is once again 25 up. Okay, so we just stack that right on top. I put the arrow so I can know where it's going, and it doesn't look like we have any more up and down arrows. Okay, so the next thing we need to do is combine all the left and rights. So we start here, we're going to the right here, 30. Okay, and the other one is going this way, 20. Okay, notice how these are going in opposite directions. This is going to become a big deal here pretty soon. Okay, so then we need to add them all up or minus them or do whatever we need to do. Notice how these two arrows are going the same direction. If they're going the same direction, we just add them. And we can see that. If we're going up 40 and then up 25, we know that we're going up 65. Okay, so if we do that, we find that we're going up 65. Now, if they're going opposite directions, we need to minus them. So 30 minus 20 gives us 10. Now we know that because we're going 30 then back, so overall we'd be back over here 10 meters, or 10 yards in this case. Then all we need to do is add in another arrow right here for our triangle. Okay, and then use the Pythagorean theorem. Once again, we'll have 65 squared plus 10 squared equals that side squared, c squared. Okay, so we get that out, and it comes out to 65.76 yards. These are the steps we'll use to solve for our crazy displacements. You'll have a few problems that I'll make you do that are some pretty crazy displacements, but it'll help you get it down. Okay, so we can also graph this. Okay, we have our distance and our time, and we can put this onto a graph, and that graph will look something like this. Okay, very good. Position versus time. Timer is there on our x-axis, and it will just continually go, and positions depend on that. Okay. Now, what does the slope mean? Well, if you remember back to when you first learned slope, they have an interesting way to remember it. They talk to you about rise over run. Okay, so in this case, that's pretty easy. Rise, which is position, over run, which is time. So in this case, our symbol here was meters and seconds. So it's rise meters over seconds. So meters over seconds is in fact just a measure of speed. Meters per second is just speed. So the slope of this position versus time graph is in fact speed. And we love that. It is speed. I know how fast we were going, and I know that since this slope is pretty consistent, notice how it's going up at the same rate, okay, that I was traveling at a constant speed. I was probably on I-15 with cruise control on, getting some very good gas mileage because my car didn't have to worry about giving more horsepower, whatever that may be. It was a pretty consistent speed I was moving. Okay. What does the y-intercept mean? In this case, y-intercept is our initial starting position. So I said we're starting here, that's a 0 position. If someone would have started ahead of me and they were, let's say, 2 meters, they could have started here. And then there were a few meters ahead of me when they started. We started at the same time, but they had like a head start. Okay. Now, can I write an equation for this line? I certainly can. Okay, we're all familiar with this equation. I also have given you a sheet with some references and graph matching that helps you give mathematical expressions for these lines. But this line is a pretty traditional line, and it's just y equals mx plus b. Okay, and so we'll use y equals mx plus b quite a bit in this class because if you get a linear graph, it's pretty nice, straightforward, and helpful. Okay, so in this case, it would be y equals mx plus b. We can then, in turn, substitute our y's and x's and m's and b's in for what we need. So with y equals mx plus b, my y is position. So I'll put position in there for my y. My x is time, so I'll put time in there for my x. My intercept happened to be, in this case, it was 0, but it could have a different intercept. And my slope, well, I have that right here. I know that it's y2 minus y1 over x2 minus x1. I just pick a couple points here and find out what my slope is, and now I can predict this graph. Okay, to help us go on. Now, obviously, this doesn't, at this point in time, doesn't seem to have to deal a whole lot with distance and displacement, but it does when you have to graph your position. So you have to graph your distance, you have to graph your displacement. You can get that. And then this is going to come in handy when we're starting to talk about speed and velocity in the next couple of lessons. Okay, so remember the difference between distance and displacement, the big concept here. Distance matters the path you took. It matters which way you went, all your quirks and turns and everything else. Displacement does not. Displacement only cares about how far are you from where you started.